Hi there, this is Chris, and as promised last Friday in class, I decided to put together a little video that went over the factorial function, the assembly for the factorial function, in more detail and with a bit less of the scrambling to figure out GDB commands. I think I've got it down at this point. So here's the basic idea, remember. Basic idea is that we've got this function called r factorial, and inside it, it obviously calls r factorial because it's a recursive function. And the question is, what does that look like when you look at the assembly code for it? Well, this is basically the assembly code. It's actually not that much code here. And let's just go through what the code says first, and then we'll actually do the example for when n equals 5, which is what main happens to call this this function with. Okay, so what's happening? So first things first, we're pushing rbx, and remember we have to pop rbx the end of the function as well in order to get the stack back to where it started, which it always has to do. And the reason we're pushing rbx is because we're about to use rbx, and because rbx is a caller-owned register, it means that we have to store it so that the calling function will get back the same value in rbx that it called the function with, because that's what it means to be a caller-owned register. It means that the previous function gets to rely on the fact that you and your function are not changing rbx, and you get to rely on the fact that the following function that you call doesn't change rbx. So you have to do this push on the stack and pop off at the end, because you have to store the value for the previous function. Okay, so then what does it do? Well, we're checking if n is less than or equal to 1. So what we're first going to do is we're going to move 1 into EAX, and then we're going to compare that to the value of, or rather we're going to compare 1 to the value of the function, the parameter, which is in this case n. In this case, we can actually just say, hey, look, n is rdi every time through the function. N is going to be rdi. Now, n will change because we're calling the function again, but it's going to do that. And then if the n is less than or equal to 1, we're going to jump down to the n, and we're going to be done. It's basically saying if n is less than or equal to 1, we're going to set the result equal to 1, which we kind of did out of order here. There's where you set the result, and then there's where you do the comparison. But it doesn't matter because it works out just fine in the assembly. And then we're going to jump down, and RAX will now contain the result of 1 when we get to 1. And so that's the base condition, base case. Okay. Now, otherwise, if we don't jump down there, we do this, and it's actually a pretty simple set of instructions here, which basically says, okay, we are going to do LEAQ of -1 RDI. This is just subtract, and then put the result back in RDI. This is just subtracting 1 from RDI. Could we have done it with a DEC or some other instruction, like a subtract 1 or so forth? Absolutely. And it doesn't really matter, though. We're not worried about why the compiler did it this way. It just happened to do it this way. So that's one way to get RDI to be one fewer to decrement it, is to just use this LEAQ and take RDI -1 and put it in RDI. So that's what's happening there. And then it's going to call r factorial. Well, what does that mean? Well, when we change RDI, we are now making n go to n-1 for this function right here. And so then it's going to call the function again, and that's happening right here. And when it returns, RAX will be the return value of r factorial n-1. Now, it's going to take a whole bunch of more calls to get that to be the case, but by the time it gets back to this call, it's going to be the factorial of n-1. And then we have to multiply it by n, which we stored in rbx. Okay, and then at that point we will also exit the function by falling through to the return, and the return result is going to be in RAX because we just multiplied it by RBX, and then that's the return value. So that's what's happening. Let's look at the code in more detail. Actually, let's just look at it in GDB itself. Okay, so if I do GDB and rfact, then we'll do this, and we can list rfact which will give us the C code for this, pardon me, and then that's it there. And then that's the factorial function. But we can also disassemble it. So what I'm just going to do, I'm just going to go ahead and run the function. And notice that we are calling the factorial function on, 5 right here. Okay, we're getting the return value in main and so forth. Okay, all right, so let's actually run it. Let's put a breakpoint on r factorial, and then let's run it. And there we go. So now we're in r factorial, n equals 5. Well, what does it mean for n equal to 5? Let's print out our di. Print our di, that should be 5. Okay, it is 5. Now, the other thing I want to show you, and in fact what I'm about to do is I'm going to draw the stack as it appears. And remember, I'm going to draw it like, I'll do it like this, like in memory, where this is like the current version of our current value of RSP points to this memory address. And then we'll just make the stack grow downwards, okay, which is what we normally do. Okay, all right, so let's look at what's actually happening. Let's look at the stack right now. Here's how we can look at the stack. We can use the x command to print out memory, and we can say x slash, let's just print 1gx right now. In other words, we're printing 1g, which is, g is a 64-bit value, and we're printing one of them, and we're just printing them in hexadecimal, okay? And if we look at that, oops, let's see, of course I need to print something. How about we print the, value of, or we print the memory at RSP, like that. There we go. So that's what's on the stack right now. Okay, in fact, I can just put that up here. I'll just put the last few, I'll put 5517E, and then we'll say there's ... There's stuff before that. 55517E is what's on the stack right now. Well, what does that actually mean? That, remember what's on the stack when a function gets called, that is the return address after we called our fact, in this case from main. So let's actually just look at that. If we say disas and then this value right here, we do that, then guess what? Take a look at where that value is. It was 55517E. 55517E is here. Oh, look, it's the address, or it's the next instruction after we called our factorial. That's what's stored on the stack at that position. Okay, so let me keep our stack up there. So that's what the stack looks like right now. RSP points to the address where the return value or the return address of the calling function is. Okay, all right, so let's actually look at what our function is here, our factorial. And here's where we are. Don't worry about this end BR instruction. It's not a big deal. In fact, I don't think it actually does anything. And then the next instruction is going to be the comparison. So I'm just going to start stepping through this. In fact, I'm going to do this so that I get the 4 instructions. I'm going to say display /4i $RIP, and this is going to give me the next 4 instructions that we're about to do. Okay, so I'm just going to step into this. So now we're going to do the comparison, and then we're going to compare. We just compared 1 to RDI, but we know RDI is 5, and the way you read this is, okay, if RDI is 5 here, then we say, and this is a jump if greater than, we say if 5 is greater than 1, we are going to jump to 55519. So that's going to be the next place we're going to go, because 1 is indeed greater than 5, greater than that. Now, this code actually looks a little, now that I'm looking at it, this code is a little bit different than the code down here, but that's okay. The compiler, different times when you compile different programs, so we're not really paying attention to this code down here. We're going to pay attention to the actual code that we're looking at in GDB, but it's going to do the same functionality. Okay. All right. So let's see. So we're going to jump down there if it's greater than that, which it is in this case. So we're going to do SI, and so we're going to go to 55519. And there it is. And then we're going to push RB. Otherwise, by the way, if it had been 1, we're going to just return there, because that's what the C code actually says. If n is less than or equal to 1, we're going to return. Okay, return because the AX is in the, we're going to move AX into the, we're going to move 1 into REX and return. Okay, so now we're going to push RBX. So remember, RBX is some value that we don't really care about right now. It's some value that main might care about, but we need to push it on there. So let's do that instruction. And by the way, if we look, and what we've done is we've changed the stack pointer, right? Let's see if we had the stack pointer up here. The stack pointer before was, let's see, where did it go here? This was a stack pointer before, E7D8. In fact, I'll just write that here. This is E7D8. That's the address of that value. Okay, that's what it was then. Now let's look at it now. So let's do this. Let's say P RSP. Because we just pushed, right? It's now going to be down by 8. So now 7D0. So it's now E7D0, and RSP is now here. Here's what I'll just do it right here. RSP is now here. Okay, and then there's some other value in there, and I don't really care what that value is. I'm not even going to print it out because I don't care what it is, right? It's some garbage value that we care. As far as we're concerned, it's a garbage value, but it's a value that main might care about. Okay, so that's where we are at this point. Okay, and now we're going to move RDI into RBX because we're saving RDI. Okay, so let's do that. Let's do SI, and we're now saving that. So if we look at $RBX, we've just saved it. It's 5. Okay, now what are we going to do? We're going to start doing our base case did not. Oops, our base case did not happen. So what we're going to do is we're going to be down here now in the code, and what we're going to do is we're going to say, oh, okay, let's just decrement RDI by 1, and then we're going to call our factorial. And let's see what happens on the stack when we do this. Okay, so we're going to decrement by 1, and then now we're going to call the stack. So if we print out RDI, it should be 4 now, right? Because we're doing 1 minus, we're calling the function with RDI, with the parameter n minus 1, which happens to be 4. Okay, all right, now if we do SI again, we're going to jump into our factorial function. We're going to call our factorial function again, and guess what? Look at this. Now we're back at the beginning of our factorial function. Okay, well, let's look at the stack for a second. Okay, first things first, let's print out the stack pointer. The stack pointer is now at 7C8. Oh boy, it's gone down by 8 more here. E7C8 is where RSP is now. Okay, and the value that is there had better be this address. Okay, it better be 551166 is the address that we're looking for. Why do I know that? I know that because I just called it from here, and the address at the stack pointer when you call a function has to be the return address of the calling function's next line. Okay, so let's actually look at that. We can do we'll do 1 again, 1GX $RSP, and there we go, 555516. And so we can put that in here, and we can say it's going to be 5.55166. That's the return of the return address for the calling function, which is our factorial. Okay, all right, so let's just go through the function again. What are we going to do? We're going to do this instruction, which you can ignore, and then we're going to compare 1 to RDI, which it's not. RDI is still bigger than 1, so we're not going to jump. We are going to jump down into our recursive case. We're going to push RBX again, right? Well, what is RBX? RBX is what we set it to earlier, and it's 5. So we're now going to push that on there, and if I do that and push it on there, let's look at the last value on the stack again. Okay, let's see. There it is. So if we're going to, right there we go. There's the value. And notice that RSP has gone down again. It's now RSP is E7, C0, and the value on there is 5. Okay, because that's what we pushed on in order to, that's what we just right here pushed it because we need to save it because we're about to change RDI. And so, or we're about to change RBX because we're pushing RDI on there. Okay, so let's see what's happening. Okay, we are now about to move RDI into RBX. Let's do that. So now if we look at RBX, it's going to be 4. Okay, and we're saving it because we're about to call another function and we need RBX to be returned to us as 4 the next time, because if you look down in the code here, we need to multiply that 4 times whatever we get back from r factorial. That's going to be 4 this time, and it's going to be times whatever r factorial of 3 is, which is what we're about to call. Okay, so let's see what happens. All right, so we just so now it's 4. That's RBX. What's going to happen next? We're going to decrement. We're going to decrement RDI and then call our function again. Let's do that. SI and then SI. All right, here we go. Let's look at the last value of the stack. Guess what? The last value of the stack is still going to be 5551166, but the stack pointer is now E7B8, and this is now 55166 ... because we have to go back again. Remember, this is a recursive function that's getting called again and again and again, and we're always going back to the same return address. So it's going to be these two values here and here are going to be the same return address, of course, but they do have to end up on the stack. Okay, so what are we going to do inside this function again? Well, same thing we always do, right? We're going to do this instruction, it doesn't matter, and then we're going to do the comparison, and it's going to now DI is 3, so we're not going to, or we are going to jump again, and then we're going to push RBX again. And if we push RBX, well, that moves the stack pointer down, and it, let's see, there it is, moves stack pointer down, and guess what? 4 is now on the stack. 4 goes on the stack, and the stack pointer is now E7B0, which is 8 fewer again. Okay, I should be moving the stack pointer down here as well. Stack pointer keeps moving down as well. Okay, so now the stack pointer is down there. Do you see the pattern now? What's going on? This is the same exact thing is going to happen for 3 and then 2 and then, and I guess, let's see, for 1, yeah, we're 1 again as well, right? We're going to get the same exact thing as we go through this. Okay, so let's just do this a couple more times. Okay, so now we're going to subtract again, call Q again. We're going to keep going. I'm going to keep going down here a few more times. I'm just hitting SI a whole bunch of times now. And let's do it one more time. Let's see what RDI looks like now. RDI is now 1. Okay, so let's look at the stack before we do anything else, because I did a whole bunch of calls again, a whole bunch of step instructions again, and do that. So this time what I'm going to do is I'm going to say x/, let's say 10gx rsp, and just see what's on the stack. So the current value of this, let's go backwards from here and keep building our stack downwards and seeing what it ended up at this point. So it was at E7B0, that was where we had 4. So that's this one. Okay, and then that means that the E7B or E7A8 is going to be here. E7A8 is going to be there, and the value is going to be again 5551166, and then oops, I think I have an extra 1 in there, 166, and then on them we're going to have 3 on here as well. Okay, and then 3, which is at this value, which is E7, let's see, it's not 98, it's going to be A0. E7A0 is 3. Okay, in fact, we need to go even further back because of the, because we did this a number of times here. So let's do this. Let's, instead of do 10gx, let's do 20. Just so we know what's going on here. Okay, and then let's see. So we've got 4, 3, and then let's see. Oh, we haven't pushed the 2 on yet. That's a good point. Let's do it. All right, we're going to do that. Then we're going to let's see. Did we actually get the 2 on there? Print out RBX is 2 now. We never needed to push 2, as it turns out, because we didn't actually have to call the calling function again. from once we pushed RB on there. But let's see. So now we just checked. What did we just do? We just compared 1 to RDI, and if we look at RDI, it is 1. So in this case, we should not jump, okay? And so what are we going to do? We didn't, by the way, if we look at our stack pointer here, let me go back and I didn't get the last thing on the stack pointer. I want to make sure that we get the last thing on the stack pointer there. The last thing on the stack pointer was another 5551166. Okay, so I should do this. 55511 or 166. This is at 0 or at E798 is what that is, and this is where the stack pointer is right now. Okay, so the stack pointer is no longer up here. The stack pointer is down here, and this is what the current stack looks like. Okay, all right, and what are we about to do? Well, let's look at our code. If we do DISAS, we are about to jump if RDI was greater than 1, but it's not, it's equal to 1. So if we do this, we now go down and we're about to leave the function. So what do we need to do? We need to move 1 into EAX because we just called our factorial for 1. And you think to yourself, wait a minute, how can we be done? We didn't do all the calculations. Guess what? We're going to now walk our way back up the stack here and do all those multiplications that we did. Right now, we've got 3 stored on the stack and 4 stored on the stack and 5 stored on the stack, and we're about to multiply 2 times 3 times 4 times 5 is what we're about to do. So let's actually walk through that and see if that happens. Okay, all right, so we move 1 into our EAX. So now, if we look at RAX, which it got 0 extended, it's just 1. Okay, we are returning to this function call down here with 1, and n is 2, and we're going to do 2 times 1. That's what we're about to do in the next, when we get back to the function. Let's see if that's the case, okay? So now we are about to do a return. So if we step into return, where are we returning to? We are returning back to 555166, right? And guess what? When you do a return, the stack pointer changes, and now the stack pointer is here, okay? And it's there. There we go. The stack pointer is now there, and let's just double check and make sure that's the case. Print RSP. Okay, it is E7A0. Look at that, it's right here. So now, by the way, did anything happen to this value? Like, did it get erased or anything? No, it didn't get erased. It's still there. If we look at E798, it's going to still be there. Let's do it. X/1GX. Let's make sure we have the value here. It's 555. Oh, you know what? There's RSP. Yeah, there's RSP. So we want to do this. We want to do that. Let's see, +8, right? +8 will give us, oh, it's still there, right? That E798 is still the value, but it didn't get deleted. It's just not part of the stack anymore, technically, because our stack pointer has now moved. But it got used to return the value. Okay. All right. So now, if we look at the top of the stack now, then let's just look at it this way. There's the top of the stack, and it's 3. Great. What are we about to do? We are about to multiply our BX, which the 3 doesn't matter quite yet. Our BX, which we saved to be 2, print $RBX, that should be 2, times RAX, print RAX, which is 1. We are now multiplying them together and putting the result in RAX, and that will leave us with a value in RAX, which is 2, and then we're going to pop RBX and return again, right? So this is actually going to happen relatively quickly. Watch this. We're going to pop RBX. That's going to change the stack pointer, right? And it's going to be now E7A8, okay? And so it's down here, which is great because we're about to return. This is RSP here. We're about to return. We better return to that previous calling function's address, the next line of it. And that's that. So then let's do that when we do the return. Okay, if we look at the stack again, guess what? It moved down to E7B0. So now it's going to be E7B0. What is in RBX, by the way? This is RSP. RBX still holds 3 because we just popped it off. And so RBX has to be 3. And then we're about to do the multiplication of RBX and RAX, right? What we're doing is we're doing the recursive multiplication here. So now we're going to do 3 times 2, and so if we look at RAX, it better be 6, which it is. And so now what we're going to do is we are going to pop RBX again. Remember, the stack pointer is at 4, so when we pop RBX, then now RBX is now 4, and the stack pointer has moved to 7B8, which is here, RSP. Notice I'm going really fast here because all we need to do is basically pop, return, multiply, pop, return, multiply, pop, return. That's all the 3 instructions do. After that we get back from calling the function. We don't need to do too much else, right? We need to do a multiply and then return. And that's it. Okay, so let's see what happens next. We are about to return again. Okay, so when we return again, we can multiply RBX. Remember, RBX is now 4. And so we're going to multiply it times RAX, which is 6. So we're going to do that, and it's going to be 24. Now RAX is going to be 24. Okay, and then we're going to pop RBX. And by the way, let's look at the stack pointer. Stack pointer is at E7C0, which is here. So we better pop off that 5 into RBX, which is what we're going to do right here. Okay, we're going to pop off the 5 into RBX, and then let's do that. Let's look at the stack pointer. Stack pointer is E7C8 because we just popped. So now it's here. That's where RSP is. And we have popped 5 into RBX. So if we look at RBX, we get 5. We are about to return right here. We're about to return. And so let's do that. And then we're going to do the multiplication again of 5 times, in this case, 24. RAX is 24. RBX is 5. When we do the multiplication, we get 24 times 5, which is 120, into our thing. And by the way, let's look at the RSP, the stack pointer, because we just popped it up. We just returned from the function, so it better be E7D0, which it is. And right, E7D0, which it is. And what do we have to do now? We have to pop RBX again. Now, I have these question marks here. Who cares what that is? Our function doesn't care what that is. Okay? We can actually look at it. I know I didn't look at it earlier, but I'm happy to look at it now, right? And this is RSP, by the way. Okay, so let's look at it really quickly, right? If we do the pop, and then we do RBX, is it a value we care about? No, it's not a value we care about. It's another, by the way, it's another, it looks like a value that was saved from main, probably saved the return value of the function that called main, etc. On there. But if we look at the SP value, RSP, it's E7D8, which is here. So it's not here anymore. It is here, RSP. And good, when we're about to return, which we're about to do right there, we need to, oops, hang on. There we go. What we're about to do is we are going to return, we better return to, remember 5517E was where main called us from. It was the address of the instruction after main called us. All right, and by the way, RAX is 120, which is 5 factorial. This is what we're about to return. We are about to return to main, and if I do that, oh look, we went back to 55517E, and that's that. And also, if we care, RSP is now going to be up here, and we are done. And as far as main is concerned, main got the answer it wanted. By the way, let's look at RSP. It is now E7E0, which is this address up here, E7E0, which is here. And again, we don't care what's in that. Main might care what's there. In fact, it should be the, well, main could have put something there. We don't really care about that right now. But what we care about is, did main get back the value 120? It did. Okay? All right. So that was kind of a long example, and I'm sorry I didn't go over it that much in detail in lecture, but I wanted to give you the entire trace through the entire factorial recursive call, because I think it's really important to understand what's happening to the stack pointer here and why all these values are going on the stack and so forth. And you want to be able to understand that as you look through assembly code. Okay? All right. Take care, and we'll see you in class.